So this video is going to help us understand Lewis structures in just a little bit more depth, specifically regarding resonance structures. So in class you were looking at carbonate and the different potential Lewis structures that you could have drawn. And you're probably pretty good now at figuring out formal charge for each of these. And so you could have quickly noticed that, okay, so we've got a formal charge of 0 on 2 of the ions and -1 on 2 of the ions. And right, that's going to be the way we're going to be able to minimize the formal charge as much as possible. Since we have a formal -2 on this ion, right, it has 2 extra electrons, we know that we can never get them all to be 0. And in fact, the sum of all the formal charges has to be the same as that. So having 2 -1s looks pretty good. We can move those to different of the oxygens, depending on which of these that we choose. And we want to have it on the oxygen instead of the carbon, because it is more electronegative, and so it's the one more likely to have that negative charge. But this gets us to the idea of, well, which of these really is best? And this carries us to the idea of resonance structures. And these come up when we have delocalized bonding. That's when we have bonding pairs that are actually spread between more than just 2 atoms, so between 3 or more. And that's different from the localized situation that we usually think of when we think about bonding, that we have 2 electrons that just sit between 2 atoms. And in these cases, it turns out that a single Lewis structure really can't properly describe what's going on in this particular molecule or ion. And so here we actually draw what we consider resonance structures. And these are all the reasonable Lewis structures that make sense. And then we're going to connect them with a double-headed arrow to really show that these things are equivalent. And so if we go back and we look at our Lewis structures for for carbonate, then we recognize that, well, all these are equivalent, and so we should represent this in terms of resonance by putting these double-headed arrows in there. Now let me just take a quick moment and say, well, we can have different drawings too. So here we have 2 different drawings of carbonate. However, in this case, this is not resonance because we've actually had to move the atoms to compare them as opposed to just moving electrons. So when we're talking about resonance, all we're going to do is move electrons around in that particular Lewis structure to get to the new one. And so if we consider this idea of resonance, there's lots of molecules that have it. Here's another one that we could look at. This is acetate. Here we could have 2 different Lewis structures that are present. And actually what ends up happening is if we look at these molecules, here we should have a negative charge on this particular oxygen. Here we have a negative charge, formal charge that's on this particular oxygen. But the reality is if we actually look at it, we look at that electron density, we have the same amount of electron density that's on each of those 2 atoms. So it turns out it looks like both of those are not quite right, but it's actually instead sort of an average. And so in general, when we think about this, the actual structure is really a combination of all the different possible Lewis structures. It's not that there was one that was right and then the other, or it's not like they change back and forth. A nice way to think about this can be to actually think of a mule as an example, right? A mule comes from a horse and a donkey. It's not a horse, it's not a donkey. It's its own thing that is a combination of those 2 animals. And the same kind of idea here. Here we've got formate. We have 2 different Lewis structures that are both viable, and we can see to get from one to the other, all we have to do is move these electrons down here to form a double bond, move these out here. And so both of these are good. And so the reality is that we actually have some combination, right? This is our mule out of these 3. It's a combination of those other 2. And this idea is really important because resonance actually leads to lower charge density, and it leads to stability. So if we consider our carbonate here, we know that we actually have the 3 different Lewis structures that we've been looking at, that all 3 of those are relatively equivalent. And if we look at the charge on the oxygens, what we identify is that there's a -1 on 2 of the oxygens and a 0 on the other one, right? So if we look here, we've got a -1 here, a -1 here, and a 0 on there. But then if we look at this next one, it turns out, well, there's a 0 here and a -1 on each of these, right? And so when we think about that, the reality is that we actually have a mix of all these. And so if we actually just consider this top oxygen, we'd have a -1 charge here, a 0 charge here, a -1 here. And so overall, the charge on that across those 3 is actually going to be -2/3, right? Because we've got 3 different Lewis structures, -1 on 2 of them, so a total of -2 divided by those 3 Lewis structures actually will give us a -2/3. So we end up with a -2/3 charge, formal charge on each one of those atoms. And that's what helps give us that extra stability. Again, we've said that the lower formal charge on the atoms tend to be positive, so that lower individual formal charge gets us something that's a little bit more stable. And for this reason, we actually see a lot of different oxoanions have resonance, and that's part of the reason that they're so common. So whether it's carbonates, sulfates, nitrates, bromate, chlorate, there's a whole set of them that you probably need to know. But stability can also mean that it's actually less reactive, so that's an interesting piece. So let's take, for example, benzene. That's the molecule shown here. We have that 6-membered carbon ring with the 6 hydrogens around it, and a couple of double bonds in there. This molecule also has resonance. It might not be immediately evident, but we can move those double bonds to between the other carbons here. And when we do that, we'll often represent that commonly as just kind of having a circle, trying to show that, well, really all of that bonding is happening simultaneously. Because benzene has 2 resonance structures, it turns out that it's actually fairly stable and relatively boring from a chemistry standpoint, in terms of it's not very reactive. But that stability is also part of what can make it dangerous. So in our bodies, we don't have a good way to be able to break it down, which is what makes it toxic to humans.